Okay, let's just briefly review what we did yesterday in the last part. Means let's start with the two-component formalism for the Klein-Gordon that we wrote in this manner. And let's look if there are plane wave solution of this equation and their form. Yesterday we proved, remember, these two-component formalism, first order in time for the Klein-Gordon at the following form. Okay, where this Hamiltonian okay, at this complicated form, T3 plus I T2 P square over 2 M0 plus T3 M0 C square, where T1, T2, and T3 are the Pauli matrices, and these become 1, 1, minus 1, minus 1, P square over 2 M0 plus 1, 0, 0, minus 1, M0 C square. So we want to see if this is a solution. This plane wave is a solution. So what we did yesterday, I'll go very quickly through this because we already did. We will plug this solution here. Now this chi0, phi 0 is the solution at time equals 0 and at x equals 0. If you put x equals 0 and time equals 0, you get these things. Now let's plug it in and let's put into this equation, and what we get is the following equation. Okay, now these are coefficient and these are the unknown quantity, because to determine this we have to. Now, in order to have a non-zero solution, because we don't want 0 and 0, the determinant of the coefficient must be different from 0, and the coefficients are these, 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 and these. So if you put it in this coefficient and put the determinant equals 0, the result that we got is that the energy that enters there must satisfy the mass shell condition. Okay, and this is an important result. That means EMP here are not arbitrary, but they have to satisfy this relation for a solution different from 0 to exist. But this, you see, is a system of two equations. The determinant is 0, so they are not independent. And the next step was, let's find the, well, first of all, from here, we derive that there are two solutions. We will call AP equal plus square root and a negative 1 with minus. We will put the index P on E because it depends on P. Now the next step is to find these eigenvalues, okay, these eigenvectors, the form of this eigenvector for the two cases. That means the positive and the negative case. So this is the equation. Now, as the determinant is 0, let's cancel here. Let's leave that. As the determinant is 0, the two equations are related, and actually they are one linearly dependent on the other. And so we can choose just one and solve one. For example, okay. Now let's see. For example, one of the equation is the following: EP minus M0 C square phi 0. Let me choose this solution. Okay, the plus. So plus, I'm choosing plus EP, the positive one. And what we get, sorry, let me just write it quicker. So as they are dependent, this equation, we get a relation between phi 0 plus. Now phi 0 plus, it means the the component of the eigenvector corresponding to the positive energy, and chi 0 plus the same. Okay. Now the relation we get from this is the following one. Then there is freedom because the equation actually are two, but only one is independent from the other. Then it means we don't have two unknown, but one we are free to determine as we like. So let's put this equal to the denominator so that it gets cancelled. If you do that, then the solution is the following: phi 0 plus chi 0 plus is equal to, so I choose M0 C square minus EP as chi. As chi, I choose this. Then as a consequence from this relation, I get this. Okay, so this is totally chosen in a free manner. Now, I go into this detail a little bit more because the book is not much detailed here. It gives to you this solution. It does not explain. This is the eigenvector, solution of this equation. The determinant is 0 because we are on the mass shell. And so only one equation is independent. Basically, combining the two, you get this relation, okay? And only one variable is independent, means the other I can choose as I like. Then I choose this to be this quantity. If you choose this to be this quantity, you see that it cancels, and the phi plus is this. So this is, but you could have had others. It's just that this is easier to manipulate because it has not any. So for E plus positive equal plus square root, I don't put the other things. The solution is this phi 0 chi, this phi 0 plus chi 0 plus mc square plus EP and mc square m0 c square minus EP. Okay. Then we can do the same for well, of course, here there are other things to determine. There is A to determine. And how we determine A? We determine A with the normalization. But let's remember that the normalization was slightly different in these two-component formalism. If you remember, the normalization was the following: d phi star minus chi star d3x is equal, A plus. Okay, so the normalization gets these things. So from here, immediately you determine, remember that we work out this normalization that with this minus sign when we work the two-component formalism. From here, immediately you plug in this expression, okay? That means this, but you have the psi star, so this disappears, and so on and so forth. And then from here, you get the expression of A plus, that is 1 over square root m0 c square square root of L cube EP. Okay, so we have determined all the components here, at least for the positive energy. Now, what about the negative energy? So let's put it here. Okay, we can do the same kind of work with the negative energy. That means in that equation that I just canceled, you plug in the negative energy solution and then work out the eigenstates. If you do that, I will just summarize the result, but I want that you understand which has been the procedure. The procedure is we found for this equation an eigenvalue equation that we have to solve. The determinant was 0 and it determined the mass energy relation. So we choose this. Now if we choose the negative energy, then the solution for this is the following. I write this here because I have to keep it phi 0 minus chi 0 minus, so plus and minus refer to the energy, is equal to m0 c square minus EP and m0 c square plus EP. Remember, there is a lot of freedom here because one is arbitrarily fixed, but I chose, as is arbitrarily fixed, I chose these values so that the numerator or the phi is simpler. And the same, normalizing, we get the A minus, and we find out that the minus is equal to the A plus. Now, what we said yesterday is now that we have these plane wave solutions, so these are plane wave solutions of the two-component Klein-Gordon equation. Now, of this solution, we will work out, this is the full correct equation. Let's work out the non-relativistic limit. Okay. Well, first of all, the non-relativistic limit of this solution of this, okay? So what we have done up to now. Well, first of all, let's do the non-relativistic limit of the energy, the positive energy. It goes C P square plus M0 C square. This we can factor out M0 C square, so I factor out this, and you get 1 plus P square M0 square C square. Am I right? C square. No, there is a mistake. So C is here and MMC square. Then I factor out, sorry, no, it's correct because I factor out the square root, so I get M0, I have a C, and I get a C square, and I get this. This one, if you do the expansion, considering the non-relativistic, it means we consider that the kinetic energy is much less than the mass energy. Then you get M0 C square 1 plus 1/2 P square to M0 square, no, not C square. And this is equal M0 C square plus P squares over 2M square. That is the usual energy things. There is the kinetic energy. So this is an approximate things. And approximating which sense? We use the relativistic limit. The relativistic limit means M0 square C square is much bigger than P square, the kinetic energy, okay? I don't care about factor of 2 and so on. Okay. Now, let's, with these things in mind now, having done this, let's calculate all these p's. And all these p's, you see, is something, if you include these and so on, that depends on p, because the energy depends on p. So let's work out for the positive energy A plus, phi 0 plus, A minus, chi 0 minus, sorry, A plus. So I have taken the plus energy solution. I am working out the plus energy solution. So plus, and I work out this. I stop. This basically is the solution if I am at x equals 0 and t equals 0. Now let's see this one. If you work out the detail, the correct expression is this. Okay, so basically is this first part I am looking at, because the other I put at 0, at x equals 0 and t equals 0. So this part disappears because I sit at the x equals 0 and at t equals 0. So this part, this exponential disappear. I have this one. Now here, let's use this expression now, that EP is equal to this. So let's insert this expression here and here. Every time I get EP, I get that. Then I get 1 over square root of L cube 2m0 c square over 2m0 c square minus p square over 2m0 over 2m0 c square. But this is nothing else than L cube. We will work out one of the two terms in a minute, okay? 1 over L cube square 1/4 V0 over C, the minus in front square. Now you see that if you take V over C going to 0, that is the true relativistic limit, you end up in this expression 1, 0. So you see of these two component things, in the non-relativistic limit, you get something that is just a very simple vector with the 1 up and the 0 down. And this is the non-relativistic limit. Now, well, I gave you the result. I just said, let's put in this, and we get this expression. But let's work out one of the two. That means let's work out, for example, this to see if this is correct. Okay, and I leave it to you to work out the denominator. Okay. Now, originally, the upper component, the phi 0 plus, was m0 c square plus EP over this quantity. Sorry, this is A plus phi plus. This component was originally that over EP for m0 c square. Now, let's insert the non-relativistic limit for EP, and we get that this is 2m0 c square plus p square over 2m0. 1 mc square comes from this, and then there is the kinetic piece. So I have one object like that, another object like that, and so I get a 2. In the denominator, I get square root of m0 c square plus p square over 2 m0, so 4 m0 c square. Okay, this is equal to 2 m0 c square plus, let's take the denominator, the numerator the same, and the denominator we factor out this part, so I have 4 m0 c square, then I have m0 c square plus p square over 2 m0 1/2. But I can factor out also this factor, okay, and put in the denominator, and what I get is equal, so the numerator is the same, the denominator becomes 4 m0 c square, square root of m0 c square, 1, so I have brought out this with the square root, 1 plus p square over 2 m square over m0 c square, all to the 1/2. Now let's expand these. Let me cancel now. Let's expand these because this quantity is very small. It's the kinetic energy over the mass energy and is very small. So if you do, you get the following things. 2 m0 c square plus p square 2 m0. That was the numerator. This numerator is this. Over 2 m0 c square. And then I do the expansion of this is in the numerator. This is a small quantity, so I get in the numerator 1 minus. So I get 1 minus 1/2 p square over 2 m0 c square. Okay, so this is the numerator. The denominator, I get these various quantity. If you take the square root, you get 2 from 4, and then you have 2 times this, so you get this quantity. Then the rest of the denominator, as this is a small quantity in the non-relativistic limit, I write as 1 minus 1/2 and bring everything in the numerator. Now if you do this calculation, you get 2 m0 c square plus p square 2 m0 minus m0 c square p square over 2 m0 c square over this quantity 2 m0 c square, and you see that these cancel these cancel these, and you are left with this over this, that is 1. So we can write it here that the A plus phi 0 chi 0 in the non-relativistic limit of V over C going to 0 goes into 1 over square root of L cube 1, 0. We have got the 1 in the numerator. Now work out at home that the denominator is as easy as this one. Okay, but that is a very important result because so as homework, work out the lower entry of the vector in 181 of the book. Repeat. Okay, work out the lower entry of the vector in 181. 181 is the formula in the book, okay? Let's do the analog for the negative energy. So we have the negative energy here. You have a minus, you have a minus, you have a minus. and we have a minus. Okay. Now we do the same as we did before, but with the A minus, phi 0 minus. So this part, but now with the, for the negative energy, A minus chi 0 minus. Now the exact expression of this we have worked out before. L cube m0 c square minus EP divided by EP for m0 c square. This, remember, comes from the A minus. This part is only this, okay? Phi 0 minus is this, and this part, together with the square root of L cube, can produce this part. Then I have m0 c square plus EP for m0 c square. Now let's do the relativistic limit. V over c going to 0, or if you want, p square over 2m much lower than m0 c square. Okay, so let's do this relativistic limit. As we did before, we work out only the numerator, but believe me, what you end up is the following: square root of L cube, 0, 1. And this is another important result that we write it here. A minus phi 0 minus chi 0 minus V over C going to 0 goes in 1 over L cube 0, 1. Okay, so you see the positive energy solution in the non-relativistic limit goes in this simple vector, and the non-relativistic and the negative energy one goes into this one. This is an important result because it has been used many times in even in particle physics. So I'm just stressing, you see, in the old times, people used the Klein-Gordon equation to study pi meson and the interaction of pi meson in the nuclei and so on. And you see that in that book, the author is a nuclear physicist. There are a lot of examples of the Klein-Gordon solving various potential. We will skip that, okay? We will only do very few things. But at that time already they wanted to know the non-relativistic limit. Later on, for pi 0 and so on, this non-relativistic limit, this form is being used heavily in field theory and in particle physics. So next year you will find that your teacher will tell, oh, you know that the two-component formalism of the Klein-Gordon, when you take the non-relativistic limit, goes the positive energy in this, the negative energy in this, and the answer, yes, we have seen, because otherwise I get complaint from people saying, you didn't do that important things. No, we did. Okay, now let for a moment, let's me write down here the expression for the okay, let me write down here the expression for the phi plus, not in the relativistic limit, but in the full things. This one was m0 c square plus EP m0 c square minus EP. You know, I did not put the A, I just put the, and the phi minus, chi minus was equal to m0 c square minus EP m0 c square plus EP. Now, the question that we will now address is the following. You see, this quantity, or also just this quantity, is often called phi of P, because they depend on P. You know, why they depend on P? They depend on P through EP. EP is this. So this is the positive energy, this is the negative energy solution. And you remember that the positive energy and the negative energy solution were related positive and negative, negative energy does not make much sense, but we proved already long ago, it was equation 1339, but I remind to you that the charge density, if you use this solution and you use that kind of things, was equal to plus minus E, EP, M0 C square, plus minus, plus minus. So you see, the plus and minus refer to the positive and negative energy, but the positive and negative energy were mapped into positive and negative charge density. This is E, the charge density. So there was a correspondence between, so instead of talking about positive and negative energy, let's talk about positive and negative charge. Then there is an operation, you see, so these that are positive and energy solution of this equation are actually, thanks to this formula, also positive and negative charge density particle. Let's see if there is a mechanism to turn one into the other. The mechanism is called charge conjugation. Okay. And that is what we will study today. Okay. Now we can actually take the full expression with everything. Let me call this expression with also the exponential in this manner. Now we don't need this anymore. So let's call these things with the full, with everything, also this P, so not just sitting. Let's me call this phi 0 plus P and chi 0 plus P. It means we have put in all the dependence. Okay, so let's take it away from here. This initial one is written there, but then there is this part. If I consider this part, then there is a further dependence on P and D. Let me call this in this manner. If this was the plus, and analogously, if it were the minus, so plus minus, plus minus, plus minus, plus minus, okay? And then you have to pay attention here, because then there is a plus minus things and the modulus in VP. Okay, and let's call this plus minus. Now, the question is, there is a manner to map one into the other. There is a transformation that map one into the other. Well, first things, it's easy to note the following. Let's remember the form of this object. Let's remember, can you see, everybody can see this here? Maybe I should write, okay, I should write them here. Let me rewrite here because we will use it. Phi plus is equal, phi plus chi plus is equal M0 C square plus EP M0 C square minus EP and phi minus chi minus is equal to M0 C square minus EP M0 C square plus EP. Okay, remember this is only this part. So let's put a 0, 0, 0. Note, I don't put a P dependence here, even if there is one, just to distinguish this object that contains all of these. Okay, so this object contains also the exponential. This object is only the first component without the exponential and without the A plus. So let's consider this object with the exponential, and then it's easy to see the following things. Take phi minus and change P into minus P. Take chi minus, change P into minus P. And this object is equal to chi plus star p phi plus star p. Now let's see if this is true. Okay, this object is this in the normal things, but we have changed p into minus p, so there is a minus p here that appear. We have changed p. Now you see immediately, note, this is the phi plus, is this. You see that the chi minus here, look at the chi minus, is the same as the phi plus here. And the phi minus here is the same as the chi plus, okay? But of course, why do we have to change the star? Because let's do the complex conjugate. If we do the complex conjugate, remember that the plus and minus have a difference here. So as here we have changed p into minus p, to get the equality not only of this part, but also of the exponential, we have to do the star. So this is the relation. Check it. It's very simple and easy to check it. Let me just do one case. For example, let's take chi plus p. This is equal to mc squared minus ep. And then I have exponential ipx minus ept. Now I have to do of chi plus, you see here, let's take this term. Chi plus I have to do the star, so let's do the star of this. The star, the star, the star. If you do the star, then this object has nothing else than a minus here, okay? Now let's take phi minus p. Phi minus p. So phi minus is here, is m0 c squared minus ep. And of course all these quantities real, so I can take away these, and these two are the same. Then of phi minus, I have to take this expression, and this expression for phi minus as a minus. With that, it becomes a plus, okay? And I have exponential. Let's see if I am right. Oh, but I have to do the minus p. So if I do the minus p, I get phi minus, and next do that, and then you get I minus px plus et. Okay, and it's exactly as this one. Am I right? Yes, it's exactly as this one. So I've taken the phi minus and I've done the minus p. Okay, so you see that the two are exactly the same, and this equality holds. So here there are three operations involved. One is complex conjugation. The second is exchange plus with minus, and exchange phi with chi. So 4 operations that are involved. Phi minus exchange with chi plus, chi minus exchange with phi plus, star. So this is the first operation. Second, take the star, or take the complex conjugate of chi plus and phi plus. So this is the second. Third, take minus p in phi minus chi minus. Okay, so these 3 sets of operation is what says, listen, this object, the negative energy eigenstate with everything. Remember, this is everything. In minus p, is equal to this other one, but the positive energy, but exchange where we have done the complex conjugation, change the P, and exchange phi with Q, phi with chi. Now, these three operations, we call it charge conjugation. That means, let's define them. You see, first of all, how do we exchange plus the chi with the phi? By multiplying by the Pauli matrix T1. T1 automatically bring the lower component up and vice versa. So if you take psi, that solution, do the star, and take the T1 and put -1, then you get an object, let's call it charge conjugate object, that is exactly that. So let's define the following operation for charge conjugation. Take your solution, do the complex conjugate, go to -1, and then multiply by T1. You get exactly from this one, you go to this one, because first, what we have to do, take the minus pi. Okay. Second, take the star conjugate. And third, multiply by T1. You get this. Okay. So this strange object is called charge conjugated object to this one. But you see that even if they are upside down, this is the particle solution, even if it is written upside down, and this is the antiparticle solution. So and vice versa, it's easy to see that if you do 2 times this operation, you get psi back. Okay? So this is called charge conjugation operation. So the charge conjugated field is this. Is a field that has the phi exchange with the chi, the complex conjugation, and pi replaced with minus pi, with the inverse of that pi. Okay. So this one is the charge conjugated field to that one, not to this one, but to the one with the plus p. Okay. Okay. So yes. What did you say?
I said, can you repeat it, please?
Okay. So I have proved this identity from the explicit form that they have, okay? And I look at them and I see what happened. Here I have the negative energy solution, but with P into minus P. And this one turns out to be equal to the positive one, but in which I have reverse chi with pi. I have done the complex conjugate and take P. So I define the following object as an object in which I take psi, whatever is psi, positive or negative energy. I do the minus pi here. I do the minus pi. Then I do the star. And third, I multiply by the Pauli matrix T1. This is the Pauli matrix. And the Pauli matrix T1 has this form. Okay. So you see it brings what is up, which is in the lower component, it brings in the upper component, and vice versa. So these 3 operations define an object. So this is the object that I define that is called charge conjugated object to this psi. Okay? Just because I realized there was this identity. So you see this object, what does it describe? If I start with a positive energy, if I start with a negative energy 1, like there, I change the sign and then I get this object. I get an object with positive energy or positive charge, so sorry, with the opposite charge. So if I start with a positive 1, I get a negative 1 moving in the opposite direction. Okay. So this is the operation that somehow, now Now, for example, you can say, oh, but it reverses the up and down, but it doesn't matter. This is isomorphic. This one, modulo this operation, is not equal, but it is isomorphic to phi plus p. Phi plus p. I mean, I have decided to write in this manner, but there is an isomorphism from this. That means once you give me this data, I know that this data correspond to a positive charge particle moving with velocity p. This one is not equal. I mean, this means there is an isomorphism between the two. That means once you give me this, I can build this and vice versa. And what happened? That this quantity, okay, is equal to another quantity that we recognize immediately. Is a quantity that is the negative energy moving in the opposite direction. So given a positive energy solution, we know that the negative energy solution moving in the opposite direction and complex conjugate of that is a solution of negative charge if we started with one with positive charge, okay? But it's exactly this object. Now, this operation is of charge conjugation does not only change charges. I will not enter into detail here. There is a couple of pages on the book. So you see here that it changed the energy, but the energy, we don't like to have negative energy. We have seen that it corresponds to positive and negative energy density. So this operation changed the energy. So the charge conjugation operation, G, what it does various things. It sends Q into minus Q, the charge, but it does other things. For example, if you take particles are characterized by other quantum numbers. When you do particle physics, you will see. So, for example, there is the lepton number, there is the muon number. The lepton number, for example, the electron has lepton number 1, and it has muon number 0. And then there is the baryon number. It tells me if it is a particle that interacts strongly or not. So, for example, the baryon number characterizes proton and neutron. And so there are other numbers. Okay, this operation, now I have only look at the charge. It reverses all the other also. Now, I will skip this part because this part you will do in more detail when you do particle physics. But what is interesting is the particle characterized by this number and the one characterized by this other number are one called the antiparticle of the other. So if this is a particle, this is what is called antiparticle. So an antiparticle is defined as a particle that has opposite charge, opposite lepton number, opposite muon number, and opposite baryon numbers, okay? This operation not only exchange Q, but it exchange also these other numbers. So the charge conjugation operation, even if it is just called charge conjugation, actually it sends particle into antiparticle. Well, antiparticles have the same mass. What is two antiparticles have the same mass. So, for example, the electron has an antiparticle that is the positron, and they have the same mass. Okay, that is one feature. But what they have is opposite charge, opposite lepton number, opposite muon number, opposite. So more than changing just the charge, it changes a lot of other features of particle. And now, what we can ask ourselves, okay, so for example, pi plus is antiparticle is pi minus, they have the same charge, the same mass, but they have opposite charge, and also all these other numbers are changed, in particular the baryon number and so on. Now let's, one can ask, what happened with neutral particle? Neutral particle does these things that, I mean, there is an antiparticle of a neutral particle. The answer is yes. And, but we have to be a little bit more careful because that is what will happen. Let's suppose the following thing. So now we study neutral particles. Well, we knew already neutral particles, what they were characterized. They were characterized by having a psi tilde real. Okay, not the psi tilde, the psi, the original psi. The psi tilde is the two components, the original psi. But if you remember, the original psi was built in this manner. Okay, so if it is real and psi real, if psi is real, it means the imaginary part of phi is equal and opposite to the imaginary part of chi. So for neutral particle, psi is real. Now, second things, for a neutral particles, let's suppose that this is what happened, that psi, that is tau 1, psi star tau, is equal to alpha psi tilde with alpha real. Okay, let's suppose this is an hypothesis, but let's suppose that a neutral particle not only has psi real, but it satisfies these things, because, well, when you do the complex conjugate, you don't get anything, it remains the same. And then this one just exchange phi with chi, and it exchange pi with minus pi. So basically you get something that is the same as a psi tilde upside down if you want, but is isomorphic. At most you could have a quantity in front, but if you have a quantity in front, let's go and see how this, we know that phi and chi were real. Phi and chi were real because the sum of the two were real to give a positive psi. So here, using these things, how we derive that this alpha is 0? Well, we will get imaginary alpha phi is equal minus imaginary alpha chi, and then from here, from these two expressions, you get that alpha is real. Now, that means here we have made an hypothesis. The hypothesis is that for neutral particle are the antiparticle of themselves modulo a factor in the wave function. Okay, so this is for neutral particle. But, okay, fine, neutral particle, and why we can accept that? Because we know that particle and antiparticle have opposite charge, so I have a neutral particle, I cannot change the charge, so it is reasonable that the charge conjugation operation on a neutral particle give the same things. That means so the statement is for neutral particle the antiparticle, no, let's write in another manner. Neutral particle are the antiparticle are their own antiparticle. Because as they are neutral, there is no charge to change, so we make this hypothesis. But these now will have some consequences that are non-trivial. That means neutral particle can have something called, let me write it here, charge parity. That means we can have neutral particle like pi 0. The photon, for example, is a neutral particle. And they are, so basically this is the hypothesis. Neutral particle are their own antiparticles. So when you do the charge conjugation, you will get the same wave function modulo a number eventually. And this number we prove that is real if the particle is neutral. But let's see is real this number from this analysis, okay, because we have this first hypothesis from phi that is real, and then from this object we go, so there is an alpha here and an alpha here, then the associated psi as an alpha, but the associated psi, we want that is the particle itself, it must be real. So we have allowed here some freedom of a factoring from, but then we get that it has to be, this quantity has also to be real, the associated psi has to be real, then we get this, and from these two, you get as a consequence that alpha is real, okay? But let's see how much it can be. Well, please.
You say that neutral particles
Are their own antiparticle.
yes, okay, so that means the neutral particle can be connected to
Antiparticle, but they are themselves. So that means, let me tell you, antiparticle, it means you have to act with the charge conjugation operation. That is how you get, charge conjugation turn particle into antiparticle. So let's take a neutral particle with a real wave function, and let's apply the charge conjugation operation. I did it. And now, as this is my statement, the hypothesis I make, I said, well, the charge conjugation is the same as the original field. So antiparticle, these are antiparticles. The charge conjugation builds the antiparticle out of a particle. By definition, I mean, I have defined antiparticle as those created by the charge conjugation operation. Okay? So it has built out of this the antiparticle, psi c. But as I have this statement that for neutral particle are their own antiparticle, it means this antiparticle must be the same as the particle, modulo some factor in front, at most.
so
Okay?
this kind of particle can exist for two states, either particle or
This is for every particle has its own antiparticle, okay?
but for these particles, they have own the whole particle.
Right. But now there is a subtle point that is where I was getting. So neutral particle are their own antiparticle. That means operation that we use to build the antiparticle, we say, look, it is the same as psi, as the normal field, but let's say same as phi modulo an alpha factor, because even if you have a factor in front, the wave function satisfies the same equation. So let's put a factor in front. First of all, I proved that for neutral particle, this factor must be real with these two steps. Now I will prove that alpha has to be plus or minus 1. Okay? Now I will prove that alpha has to be plus and minus 1. How I prove it? Well, it's very simple. We know that the charge conjugation operator, if we do 2 times, we should get back to psi. We proved it before. But this, what does it mean? This means alpha square psi tilde equal psi alpha. Why? Because the first time we do a charge conjugation, we inject an alpha on a neutral particle. Then we do again, so we get alpha squared. But from here, alpha is real, so it's not a phase. And from here, we get that is equal 1. So alpha is equal to plus or minus 1. Then, when we do the charge conjugation, we can either get plus psi tilde or minus psi tilde. This number, plus 1 or minus 1, okay, I'm talking about neutral particle. If I allow to have a number here, and I am allowed because, most of the I mean, there is some freedom after all. This, if this is a number, it satisfies the same Klein-Gordon equation, so you can allow them. You can say, well, let's put just a phase. But from here, as it was a neutral particle, I proved that that must be real. Second, I proved that alpha squared must be 1 from this relation. If I do the charge conjugation of a charge conjugation field, I get the normal field. But for neutral particle, doing the charge conjugation means just multiplying by alpha. I do 2 times, I multiply by alpha square. Okay? It is real, so no stars involved. And then from this relation, you get that alpha is equal 1. Alpha square is equal 1, so alpha is plus minus 1. So when you do the charge conjugation of a neutral particle, you can either get psi or minus psi. This number, plus 1 or minus 1, is called charge parity. So neutral particle have a further quantum number, that is the charge parity. The charge parity can be plus 1 or minus 1. Now, in fact, when you take the booklet with all the particle data, you often see that to pi, they associate some number, spin 0, and then plus, and they put a plus here. That plus, so if the particle is a neutral particle, you have to specify its charge parity. If a particle is positive, then there is no charge parity, because via the charge operation it goes into its antiparticle. But when you have a pi 0, via the charge operation it goes in pi 0 because of that statement. But the point is, there is a further number to specify, because it depends if it goes in psi or if it goes in minus psi. And that is the charge parity. Okay? So inside neutral particle, even if they are, each is the antiparticle of itself, you have to ask further, okay, one is the antiparticle of itself, but which is the charge parity? That means when I do the charge conjugation operation, do I get a plus psi or a minus psi? Okay, so you can say, well, it's irrelevant. No, it's not irrelevant. Now I will show to you why it's not irrelevant. Okay, so this charge parity, so this is the charge conjugation operation, it's send particle into antiparticle. This is the charge parity. It applies only to neutral particle. Okay, so it's a further quantum number that applies only to. Now let me give to you an example. Let's do a little bit, please.
These particles, we have at the same time like particle or antiparticle.
Right, exactly. But you have to be careful that if, when you use them as antiparticle, can you use the same psi, or you have to use minus the same psi? If you were doing quantum mechanics, normal one-particle quantum mechanics, it would not matter, because, you know, it's modular phase, and all the wave functions are always modular phase. But when you do second quantization and you will have many particles interacting, then this plus or minus will matter. And I am going to give to you. So they behave in the same manner, but the antiparticle you have to describe with the minus, if its charge parity is minus 1. So they give you a neutral particle, fine. Its antiparticle is the same, but you have to ask, then when you do calculation, you have to ask, listen, which is the charge parity? And then that guy, I know it's neutral, but you have to give me the charge parity. Is plus or minus 1? You have to ask this further question for neutral particle. Because if you have to use minus psi, then things in some calculation might change. Now I will show to you a neutral particle that has charge parity minus 1, is the photon.
Okay. In this case, why this particle doesn't annihilate? Because we know that if we put a particle and an antiparticle, a corresponding antiparticle together, they annihilate. So here we have one particle, but
Yeah, the problem of annihilation is a problem of second quantization. So I don't want to enter that because we will not do end of particle physics. That means here nowhere I have given to you the formulas that tells you that a particle and an antiparticle annihilate. Okay? So you understand the point. You know from the literature, from having read books, that particle and antiparticle, when they meet each other, they annihilate and they go into photon, okay? But you have to build the formalism for that, and the formalism for that you will build when you do field theory and second quantization next year. I have not given you that formalism yet. So now you are asking me, what happens when I have two neutral particles? For example, I take the neutron and I take the anti-neutron. Do they annihilate? You will get the answer next year. I don't want to go into details of that.
Because for each particle we have two behaviors.
Right.
Particle and antiparticle.
Yes, and they can have this number, but you will see that they will not annihilate. This number is important for the discharge parity, is important for the to take account to take account of the interaction, and I don't want to enter that. Is a very delicate and complicated technical things that you need to have the tools of second quantization. Okay, so just the information I'm giving to you now is the following. If you have a charge, if you have a neutral particle, then there are two further numbers that characterize that particle. Is the charge parity. And it can be +1 or -1 for neutral particle. That is the only information I want to give, because the rest of the formalism is, I mean, we don't have the tools. I mean, you need 1 year. You will get at the end of field theory of particle physics with these things. And okay, let me go on this because we are quite behind schedule, unfortunately. But yes. The charge parity, now I'm going to give an example. Okay, basically is this number, you know, is something like saying, yeah, what is the baryon number? What is the baryon number? It's a number that you assign to proton and neutron and so on and so forth, and to pions, and for example, electron, you give baryon number 9, but it's a convention that we have. It's a convention, and then once you have given this quantum number, you ask if you ask yourself if that number is conserved under some interaction or not. Okay? So let me cancel and let's stick to this. Let me cancel this. Now, well, it is being proven that this operation of charge conjugation, let's call it as an operator, and you know what it does. This operation of charge conjugation taken on a psi tilde, it does the following: tau1 psi tilde star and send p into minus p. Okay, this operation commutes with the Hamiltonian of strong interaction. So the nuclear interaction are charge conjugation invariant, and the same electromagnetism. Electromagnetism is invariant under, so the interaction via photon is invariant, but not the weak interaction. The weak interaction, if you have neutrinos, if you have particles that have weak interaction, the charge conjugation is not a symmetry there. Okay, you will see when you do particle physics. This is just phenomenological information I want to give to you. But now let's take the following three neutral charges. So charge parity. Let's take the photon, let's take pi 0, and let's take the eta meson. This is the pi meson, this is the eta meson. This meson is much heavier, is 548 MeV, and this one, you know, is 134 MeV. They are all three charge neutral particles. Now the charge parity. The charge parity is -1 for the photon, 1 and 1 for this. Now let's see if this is consistent, given these numbers, So usually you give an assignment of numbers. So this is the charge parity. Let's see if this is consistent with what we said before. Well, for example, some of the decay that we see in nature is eta 0 that goes into gamma. Or we have eta 0 that goes in 3 pi 0. Or we have eta 0 that goes in pi 0 plus gamma. Or we have pi 0 gamma plus gamma. You see, all these are strong interaction. It means nuclear interaction. Let's see if the charge parity is conserved. Yes, 1, and here I have -1, -1. You multiply, you get +1. Okay? The quantum number get multiplied when you have product. Here you have 1, so you have 1, and here you multiply. If you have more than one particle, you multiply and so you have 1, and here you have 1. Here you have 1, here you have -1, -1, you multiply, you get +1, multiplied, you get +1, the same here. Now, what is anomalous is this. Why they gave this strange assignment to the photon, that the photon has that strange things. Let's take the Lagrangian of electromagnetism. If you take the Lagrangian of electromagnetism, you have the interaction is the electromagnetic current, mu, multiplied by the gauge field A mu, plus the dynamics of A mu, okay? The Lagrangian is always this, that you have a fork current, an electromagnetic fork current interacting with the 4 vector. Now, there are evidence that the electromagnetic Lagrangian is invariant under charge conjugation. So if we do L electromagnetic, C to the -1, this is invariant. But let's apply it here. We have C, J mu, electromagnetic, A mu, C to the -1. But now let's insert here a C to the -1, C, A mu, C to the -1. Now, the electromagnetic current is made of charge particles. So, under the charge conjugation, it goes into J mu, because it's made of charge particles. But then this object, for the Lagrangian to be invariant, because this is equal to L, then this one must go into -A mu. So, you see, the photon is one of that particle that when you apply the charge conjugation goes into its opposite field. Okay? So remember, so some people say that the photon is not the antiphoton of itself. That is not the right statement. The photon is the antiparticle of itself, but with charge parity -1. That means when you change the particle into its antiparticle, you have to multiply by a -1. Okay, that's the only things. Okay, please. These are decay that we see in nature. It's not definition, it's a decay that we see in nature. We see that this heavy meson can decay in this manner, can decay in this manner, can decay in this manner. These are all channels, people say, in which particle can decay. And these decays are consistent with this choice of charge parity. Okay. Now, before going back to this, there was, we will go and do these things, but let me go back to that non-relativistic limit for the moment. So charge conjugation, one could spend many hours on charge conjugation, but you will do that more in particle physics. So it's part of the program, but it's not really my main goal. The goal of this course is to study relativistic equation and not so much the property of particle physics. Yes.
How do you explain the strange behavior that we have in commutator relation? What about if at H the Hamiltonian is on the right, we have the strong Hamiltonian, and the negative part we have the electromagnetic.
No. Maybe you misunderstood me. What I'm saying is, imagine you have an Hamiltonian, and imagine now that you want to do a rotation of it. You know that basically what happens is you take the generator of rotation and do the commutators, right? You have learned that from quantum mechanics. If they commute, it means rotation is a symmetry for the Hamiltonian. Okay? This means also that if you do AJ theta, H, A minus J theta, you get the same. This relation is the same as this one. Okay? Now, instead of that, let's consider, instead of a rotation, the operation of charge conjugation. Then, if an Hamiltonian is invariant under charge conjugation, you get this relation, that is the analog of this. Or this is equivalent to saying that CH is equal 0. Okay? Now, the part of interaction that is called strong interaction, that affects mostly the baryons, is invariant under charge conjugation. That means people experimentally have seen that the Lagrangian that we use for strong interaction, that is the Lagrangian of QCD, is invariant under that operation of charge conjugation. And the same for electromagnetic interaction. So the electromagnetic interaction, that is the interaction of every charged particle with the photon, is also invariant. So that is what I meant, okay? And it's the analog of this. You have an Hamiltonian invariant under the rotation, it means this. So now call this, instead of rotation, charge conjugation, and you get that the strong interaction is invariant. The Hamiltonian of strong interaction is invariant. And the Hamiltonian of electromagnetic interaction is invariant under charge conjugation. That is what I wanted to say. Okay? Now, let's abandon these things for a moment because it's not central in the program. You have seen that when we had psi tilde plus, and it was phi plus, chi plus, p, at the end, you remember we had an relation with the exponential and so on, but at the end we called that in this manner. And you have seen that this one in the non-relativistic limit goes into something that is 1 over square root of L cube 1, 0. And that the psi minus phi minus p chi minus p all in the non-relativistic limit goes into this one. Well, one could ask, okay, you get that in the non-relativistic limit, but if we call this object phi, so this is phi plus and this is phi minus, can we get a transformation that send the psi tilde plus, an operator that applies to phi tilde plus, send me into phi plus, that very simple vector, and the same for psi minus? Does it a unitary, not a unitary, some transformation like that exist? We got in the non-relativistic limit these things, but does it exist a transformation? Well, as we are in the non-relativistic limit, we are losing a lot of the dynamics. So this transformation cannot be unitary because the dynamics of these are totally different than the dynamics of this. So it cannot be unitary. And in fact, it's been proven that U exists but is not unitary. And it was built anyhow, because it's not difficult to build it. This U is the following. I, the identity operator, M0 C square plus EP minus T1, tau 1, the Pauli operator, M0 C square minus EP divided by 4 M0 C square EP. Well, by the way, here there is also, of course, the exponential. So the things exist, but it's not unitary. And who found this operator that map this into this very simple one? Well, were two physicists at MIT. One was Feshbach. I never remember if there is a K or... No, there is an H. Feshbach and Villars at MIT in 1959-58. Okay. How many of you are already taking the GRE exam? Take the GRE exam and score up 1%, huh? Then you go to MIT. I see that you laugh, but you have to do, I mean. And there was a question, please. Somebody asked. The name, you mean?
No, conclusion. Okay, yes.
This is the identity operator in 2 dimensions. 2 by 2 identity operator, this is Taiwan. All of you already know where you will go next year into the normal diploma course here. I mean, then you have next year to take the GRE, so try to take the GRE and get upper 1%. And then you will go to MIT to do your PhD and so on. Okay. Now, one last thing that we will do, and then we will continue next week, is you have seen the photon and the fact that it has charge parity. This is all on the book, but on the book, oh, by the way, on the book there is a lot of things on the, so I would say for the Fesch-Villars thing, just study what is on page 32 and not the full thing, just to understand what it does, okay? So just page 32, not the full section, because there are a lot of things. This guy is a nuclear physicist, Greiner, and he loves these 2 guys. This was the head of the nuclear laboratory at MIT later on. He was very young when he did this paper. There is another nice book on mathematical method in physics. And Villars was a former student or collaborator of Pauli, so they did these things. Now what we will do is, you remember that when you have interaction with an electromagnetic field, in the Schrödinger equation you use what is the minimal coupling, and the same happens for the relativistic case. You use the analog of the minimal coupling. So most of you have already seen that there is, you can introduce AX and AY and AZ for the electromagnetic potential. This is the electromagnetic potential. You can introduce a 4 vector, then this A0 is related to the normal electric potential, for the normal electric potential from which you derive the electric field, and this one via his rotor is related to the magnetic field. Okay, so there is a 4-vector notation also for that. And then how do you couple if you have an electromagnetic field interacting with charged particle? How do you, oh, by the way, you can also do the following things. Raise these as G mu nu A nu, and then what you get is A0 minus A vector. Okay, so you can introduce for the electromagnetic potential a 4-vector. Then how do you couple the things? So you do the following. You replace the derivative with respect to t with IH, the derivative with respect to t, minus E, that is the charge of the particle, times E0. And you replace the minus I gradient that enter our equation with minus IH tilde minus E over CA. Okay, this manner, so the electromagnetic interaction is introduced by this simple replacement, and this is called minimal coupling. Okay. It is very analog to what you do for electromagnetic non-relativistic, for the Schrödinger non-relativistic equation. Let's see now what happened, then we stop here. Let's see what happened for the Klein-Gordon equation. Well, the Klein-Gordon equation basically is P mu minus M0 square C square psi. Now, if I turn on an electromagnetic interaction, then I have to do the minimal coupling replacement, and that means P mu minus EC A mu, P mu minus EC A mu psi equal M0 square C square psi. Okay, so this is the, if I have a particle moving just as a free particle, but it's charged. And now I turn on the electromagnetic field. The manner to get the interaction is this. You can ask why it works. I mean, when you postulate an equation, it's just that you ask why. It has to respect some symmetry maybe and so on. And here, let's say the minimal coupling that was discovered by Dirac, if you do that minimum substitution, it works. It gives the right interaction. And if you work out now the various components, you see here we have added to ddt this term, but actually here, if you use the P0, there is a C, so there should be a C here. That is why the general coupling P0 is not ddt, is 1 over C ddt. Okay, so now if you work out the components, you get the following thing: 1 over C square IH ddt minus EA0 square psi equal IH gradient plus ECA square plus M square C square psi. So this is the Klein-Gordon equation for a charged particle in interaction with an electromagnetic potential A mu. Now, next time, what we will do is we will discuss the gauge invariance of this equation. We will see that if we properly transform the wave function, and there is a mistake on this book, unfortunately, if we properly transform, then this equation is gauge invariant. Okay, but we will do next week.